In this video, we're going to build off of the last one where we calculated and plotted true stress and true strain for a metal. Here, we're going to build that into determining strain hardening. So determining the strain hardening of a sample. So what is strain hardening? So strain hardening is a material's ability to strengthen while we're straining or performing a tensile test. This is the same as cold work. So if you're rolling or extruding or any other type of cold work, this is a form of strain hardening. And so what we, how we can kind of show that and the representation of strain hardening is an increase in the strength with the engineering strain down here. So two examples here. So I've got a orange curve here, and then right at this point is where the plastic portion of the curve begins. And you'll notice that it goes up slightly during this region, right? Very slight. However, if we look at this blue curve, the plastic region starts somewhere around here, and you'll notice that this increase in strength with strain is quite a bit higher. So a higher slope in this plastic region indicates a higher ability to strain harden. So what that means is it doesn't necessarily mean a material is stronger. It just means a material can become more and more strong with this type of strain. So like I mentioned, this is going to be based off of true stress and true strain curves. So here I'm showing the engineering, but we're going to work with the true stress and true strain we built in the last video. So how do we get this information? Well, we need to take that plastic region and fit the data. And so we can fit this data to obtain a couple parameters, the strain hardening exponent and a strength coefficient. So this is our fit. It's an exponential form. We have the true stress indicated here is equal to K times epsilon T, so true strain, raised to the power of N. So let's go through these. So again, in the previous video, you saw true stress and true strain, so sigma and epsilon T. And then these are our fit parameters, so K and N. K is basically a scaling factor, so this is related to the material's strength. This one is usually not desired as much, but the one we really want is the strain hardening exponent. This is essentially the parameter that tells us how much ability we have to strain harden. So typical values. These will be helpful as we go into the Excel sheet and look at our data. So for metals, these can be anywhere from 0.1 or so up to 0.5 for the strain hardening exponent. And so what those mean is they're related to the slope of the curve. So low values mean low slope, and so that means that a material strain hardens less, and a high value indicates that a material can strain harden more. So those are going to be useful when we get to the next step. So now we're going to transition over to the Excel sheet. We're going to start with the true stress, true strain curves that we developed in the last video, and we're going to fit and find these parameters for strain harden information. So let's switch over. All right. So if you watched the last video, you'll recognize this spreadsheet. This is an example we're going to use with 4140 steel. And in the last video, we dealt with a sample that was quenched and then tempered at 200 degrees Celsius. So that's the one we have here. You might recognize the data that we have. So we're going to work with that one. That's the first one. But as a comparison, to show you some different information and show you a comparison for strain hardening and what this means, I've also got a second temper. This is the same 4140 steel. It's been quenched, but in the case of the tempering, we've tempered at 700 degrees Celsius for a much longer time. So this is to give us a comparison for strain hardening. And so I've gone through and done the exact same thing that we did in the previous video for true stress and true strain. And that's what I have over here, with the blue being engineering and the orange being true stress, true strain. So now what we're going to do is we're going to take that data and we're going to process it through to get strain hardening exponent for both of these samples. So how do we do that? First step is I mentioned that we want to fit the plastic region. So this has the plastic plus the elastic region. So we need to separate the two. And so what I'm going to do is first find the linear portion, so the linear elastic. So I'm just going to add another one up here to do this. And the reason I want to do this is because I want to find the linear region for this curve, which has a gradual transition. So I want to find the linear region, I want to find the elastic modulus, and I want to fit that, and I want to do the offset so I can determine where my yield strength is and cut off all the information before that. So it's a few steps here, but I think it's useful to show this. So we're just going to duplicate this data over here and copy it down. All right, and then what we're going to do is there's a pretty gradual transition between the linear and the plastic, which is nonlinear. And so what I'm going to do is I'm just going to kind of arbitrarily cut off at about 1,000 on the stress axis. So I'm just going to go down here, and this is just to get a rough distinction for this so we can get a good linear fit. So I will plot this just so we can see this, what this looks like. All right, and if you see now, this second plot we have down here is very linear. And so I'm gonna right click, add trend line. Excel can do a linear interpolation very well. And so I'm gonna add a linear interpolation. I'm gonna do this automatically. I'm going to have it display the equation and show the R squared for quality of fit. So let's see what we got. All right, so let's move some stuff over. So this is our linear region. You'll notice that the fit is really good, 0.9991, and then we have the fit value. So this is our fit, this is our, and then the value in front of the X is the elastic modulus. And then we have the Y equals mx plus b. The m here is the elastic modulus. The b is the what causes it to shift one way or the other. So that's our slope. So again, what I wanted to do was find that so that I can do the offset method. So there'll be a different video to determine the yield strength by offset method, but we'll just kind of go through this kind of quickly with this. And one thing I'm going to do is I'm now going to, let's insert, that's not where I wanted to do it. Let's insert over here. So after the engineering stress strain, and I'm going to do the 0.2% offset. I'm just going to add that as column. This is also going to have the same units of stress. So this is going to be our fit. Essentially our linear slope that we had over here. So I'm going to just copy this over. So this is going to be 1845.78 times X. So that's going to be the strain plus 42.478. So I'm just copying this over and into a sheet here. So basically this gives me the fit. So if I come back up here to this plot and add yet another thing, this is going to be our 0.2% offset. All right, I'm going to do that. This might look a little odd because I'm adding the whole thing. Yeah, so there's going to be a lot of extra stuff I don't need to, but I'm just going to adjust the axis here instead of going through some other things. So let's just do that. Let's do just the axes here. Oop, that's not what I wanted. Doing this in real time, so there we go. All right, so now we have our information. So right at this point, what we've done is we've actually just fit the linear region. You'll notice there's no offset, and so we need to build that in. So we need to build in the 0.2% offset. And so there's different ways you can do this, but what I'm going to do here is just a very crude addition to this, and I'm just going to subtract. It's going to be a subtraction here, and it's because it's 0.2, we need 0.02 to be the offset because it's a percent, and so we're just going to do that, and we'll see how that works. See if I did my math correctly. Yep, here we go. So you'll notice now, this might not be the most efficient way, but I'm going to show you this. This is how I'm going to do it for this example. Sorry for the cat in the background. So now what we've done is we have the offset, the green curve you see here. And what I can do is I can just replot this a little bit just so we can see it better. Let's go like this. Lots of noises today. We've got some kids playing in the background. All right. So we've got it here. We've got this offset. And so again, the whole idea of doing this is we did an offset. This gives us our yield strength, which is where we get noticeable plastic deformation. And so this is kind of our cutoff for elastic below and plastic above. So this is almost exactly at 1400. And so we're going to use that now to take that data and essentially eliminate anything before 1400. And so I've actually already got that data in this section in this new sheet. So what I'm going to go to is I'm going to scroll down until I get to 1400. And I'm going to go back up, and I'm just going to delete everything. Again, that's the elastic portion. It's not part of this. So essentially that's what we're going to do. All right. So that is, we got rid of the first one. So that was this 200 degrees Celsius one. So now I'm going to switch over and we'll do the kind of same operation for the 700. Sorry. So one thing you'll notice here is that this isn't a gradual transition between the linear and the nonlinear portion that we see in the other curve. We actually have what's called a yield point phenomenon here. And so the lower yield point actually determines the yield, what is the yield strength. But again, this video isn't about that. It's just about the transition. So what we're going to do is we're actually just going to eliminate everything. So the linear portion here up to where you see this transition. And this one's actually a little easier because what we can do is we can just zoom in a little bit so we can see this better. All right, and then we'll just find this point. And so this is 0.035. So I'm just going to write that down. And again, I'm going to do the same thing. So I'm going to go back to this new data sheet that we have. And on the strain axis, I'm going to erase anything before 0.035. So just some scrolling here. All right, and I'm going to delete it. Perfect. All right, so now what we have is we have the true stress and true strain for these two. Now we're ready. We have the true stress, true strain for these two samples, only the plastic regions. And so now we have the raw data set up to compare to our expression for strain hardening. And so we're going to try to fit these two samples for that. So we'll come back in a second and we'll go through that operation. All right. I'm back here, and what I've done is I've just rearranged stuff a little bit so that it's a little easier to read. And so here I've separated out the two curves again so that we can concentrate on each for fitting purposes. So we're going to work with a 200 degrees Celsius data. Again, we've already processed it, so it doesn't have the linear elastic portion. It's true stress, true strain, and that's what we're looking at here. I've done the same for 700. I've split it up into this other formula. And so now we only have that data. And so we're going to go through how we fit this. So again, we're going to make a new essentially fit column. So let's call this strain. Let's just call this fit. So this is going to be our fit data. This is going to have the same units of stress. And so this is going to be our equation. So here what we're going to do is we're just going to input what our strain hardening exponent equation is from the slides. And so that was K multiplied by the true strain raised to the n power. So a couple things, and let me actually add some columns up above. Oh. Let's get out of this. So I'm going to back up a little bit, and I'm going to add a couple more just for this purpose. And so we're going to add something up here called K, and we're just going to put a number up here. We'll come back to what this is in a second. And then we're going to have another one called N, and we're just going to put a number here. So this is just, these are going to be the parameters for the fit. And we're going to come back with the information later, but let's just start with that. So back to this. So now using that expression we had from the slides, it was K multiplied by the true strain, so this column, raised to the N. So both C, the K term here, is going to be fixed up there. And the only thing that's going to vary is true strain, right? Because we want to essentially calculate it here. So this is essentially us fitting what we think the data is. And our parameters up here are our initial guesses, right? So we're going to have that. So what we want to do is we're going to come over here and fit this. So we're going to just plot this fit, I should say. So same thing, same X, but the Y is going to be different. The Y is going to be our fit. All right. Then we come back up, and you won't be able to see it because we've guessed badly initially. But let's just zoom out and just have that auto. So now our real data, our experimental data is the blue, and our fit data is here. So the parameters that I just put in here are obviously not good fits. And so we're going to come back to this. But basically what we want to try to do is we want these to converge. So that's what Excel does with a linear fit. But if you're trying to do more complex fitting, it doesn't have a lot of options. And so we have to do this a little bit more manually with something I'm going to show you here. So let's add a couple things here that we're going to use. So the first one is going to be what I call residual. So this is the fitting term, which is the fit data. So basically the orange curve minus the real data. So that's all it is. So it's basically a delta or a difference. And so you can see here that the residual, the difference is pretty large, 775. So it's pretty far off. All right, so then what we're going to do is we're going to square the residuals. So all we're going to do is take this and square it. So that's going to be even larger of a number. And the reason we're going to do this is we're going to take the sum of those squared residuals, so I'll just call it SSR. And so we're just going to take the sum of all these terms. All right, so this is a huge number right now. And so what we're doing is we're basically building in a fitting protocol for us for this equation that we have for the one that we've labeled here. So this is really critical because when you're doing a linear fit of your data, Excel can handle a lot for you, and it can be pretty easy to do. Here, though, when we're putting this in manually, our initial guesses become very important. So here I've just picked numbers out of thin air, but a couple of things you're going to want to do. So to get a good fit, you want to have these as close as you can, right? You want to have good initial guesses. And so there's some different ways you can do that. You can kind of look at the data and you can make some interpretations based on the equation itself. So kind of knowing a little bit more about this exponential form, you might be able to make some guesses. You can look up some values, which is what I've done. So for example, I looked up the values for a 4340 steel, and it was a value of 640 for this K value, and the N was 0.15. So you can see this is even farther away, right? So this is also not a good guess. So based on that, we can determine that our N value is going to be pretty low. So I'm going to move this back down and maybe call it 0.08. Let's see what that happens. And then we know this needs to be higher. So just based on, the values we have here on the strength axis, we're between 15 and 2250 or so. So let's just pick somewhere in the middle. Let's go 2000 just to see what happens. Okay, that actually is starting to get at least the two closer together, right? You can start to see they're closer. The slope doesn't really match, and so we can, again, try to just tweak this a little bit and see what happens. Okay, so it looks like maybe our slope needs to go in the opposite direction. It looks like it might even be higher. So I think we're going in the potentially the wrong direction here, but you can see I'm just kind of trying different combinations just to get a good initial guess, and this one is really far off. So let's try a couple more just to see. Okay, so I'm going to go back to maybe 2000, and I'm going to change this up a bit. All right, so I'm just going to get it close enough here. Again, I'll see. We'll see how this works, but we have it pretty close. And so the step now. So obviously, trying to do this by hand, trying to reduce this number, which is what we're trying to do to make this fit as close as possible, is not going to be possible by hand unless you have thousands of hours. So we need to do something to get this. And so what we're going to use is called Solver. So we're going to go in here, and if you click up on data, you'll notice it's up here. If it doesn't show up for you, you can go here and go to properties, I believe, and make it show up there as well. Oops, it's not there. But essentially you have to add it. So you have to have this solver here. I can put a follow-up on that if you don't have it. But essentially in add-ins, you need to have it clicked for solver add-in. But I've already got it here, so we'll just kind of go from there. So I'm going to just, again, go to data. And then over here for me, it says solver. There's different ways to get to this, but you just want to get to solver. So I'm going to open this up. And what you'll notice is that it says set objective. So we want to minimize, we want to lower this number so that our fits are closer together. So I'm going to select that box, which it was already selected for. And our objective, again, now is set for max, but we don't want to maximize this. We actually want to minimize this. We could also set a value of 0 as well, but minimize is probably the most accurate thing. And so it's going to solve or try to minimize this by changing variables. And so we want to do that by changing K and N. So we're going to hit this button so that we can select both these. So these are our two fit parameters. So this is telling us that we're going to try to minimize this SSR, so the sum of squared residuals, by adjusting K and N in this parameters. So that's all we have to do. So it's going to do the rest with this. And you can adjust other parameters if you want, but we're going to stick with this pretty simple. And we're going to see if this works, see if our initial guesses are good enough. All right. So now you'll see that it did its job. It says, do you want to keep it or restore the initial values? If you look up at this graph here, you'll notice that our fit is pretty good. It's a lot better than what we had before. So this is great. So I'm going to hit OK. And we'll start with this and see how that works. So coming over here, you'll notice that this SSR went down. It's still pretty large, but it went down. And then we have our values of K and N. So you see I was pretty far off. The K value here is 4,000, and then the N value is 0.21 approximately in this example. You can also see that the fit isn't perfect, right? If we replot this, we can kind of see that this isn't the best fit. You can see it doesn't fully match the slope that we have in this example, but we'll kind of take it from here. So again, keeping this in mind, let's go about this and keep this 0.21 number in mind. So I'm going to do the exact same thing for 700, and we'll come back to this. All right, so we're back here with the second example. This is the 700 degrees Celsius temperature. We've essentially done the same thing. We've added the fit with K and N. We've calculated the residuals and the squares and the sum of residual squares. And we've gotten a first initial guess. I used the same value for N, but then I changed this a little bit. And you can see that I'm actually pretty close, and the shape is pretty close as well. So we'll do the same operation. We'll come up here to Data, Solver, select the sum of squared residuals to minimize, and then we're going to change our variables K and N, which is what we have. And we're going to, again, solve this. And again, you see that it's resolved this in this case. And here, we've got a much better fit. So our K value is 976. So that's our strength coefficient. And our N value is 0.218. So it's very close to the last one. And we've minimized SSR pretty well. So you can see you don't see much daylight between these two curves. So this is actually a really good fit. So again, the slope here, the N, the lower this is, the less ability it has to harden. The higher that number is, the more it has ability to harden. So this is just telling us the slope. So the higher this value is, the higher the strength here. So with that in mind, let's go back and revisit the 200 and see if we can make this any better, because we can tell it's not a very good fit. We're trying to troubleshoot this 200 degree sample that didn't have a very good fit. And I'm going to try one last thing and see how this works. So you'll notice that I've actually already adjusted the data a little bit. I've taken out that little dip that was in our data. That didn't have much effect. But before the dip, you'll notice that the slope is quite a bit different than after. So again, this was due to the extensometer. And so based on this, what I'm going to try in this example is I'm going to try to take all the data below about 1900, so below where the extensometer was, to see how that affects this fit. So I went a little too far. Getting close. Okay, so here. So I'm going to try this, delete this, and it looks like maybe I deleted a little too much. So let's undo that. I was using the wrong column here, so I want to look at this B column. That's where my data is. So I'm going to delete everything under that. And let's see how that works. Okay, so you see I got rid of everything that was in front of that data. So now let's try this one last time and see how this fit goes. So data, solver, I'm just going to go back just to make sure, and select our two parameters here. And I want to minimize it, and I want to solve for this. All right, so now you can see behind the scenes that our fit is much better that we have here. All right, so yeah, so something about the data before the extensometer was removed means that we didn't get quite a good representation of the data. So I might follow up with some more specifics about that. But for now, let's just kind of note what we have. And again, the strength parameter, I'm not going to worry too much about, but the strain hardening exponent. So this again was for our 200 degree sample. So a value of about 0.13 for the strain hardening exponent means compared to the 700 where it's about 0.21, so a lower value for the 200 degree sample means that it has less ability to harden during this test. So this slope is lower, so it doesn't harden as much during cold working. So this is a good piece of information to have for processing as well, because this tells us that if we cold work this material, it won't harden as much. And usually what that means is it's already a very hard material, and so we can't harden it anymore, or less so. As opposed, and you can already see it just comparing these two curves. This is a steeper slope represented by the 0.21 number. So this tells us that this 700 sample can be cold worked and hardened as it does so. So it hardens more and more. The change from 500 up to 700, as opposed to, on this case, we went from about 19 up to 22. So it can't harden quite as much. So again, important information when you think about cold working. So hopefully that demonstrated how we can use Excel to determine the strain hardening exponent and strength coefficient, so fit parameters, to give us information about strain hardening or cold working of a material.